My name is Mark Laing and I'm head of the Computational Fluid Dynamics team at TÜV National Engineering Laboratory. Throughout my career so far, I have around 15 years experience across various different industries such as nuclear, oil and gas and renewables. Computational fluid dynamics is a branch of fluid mechanics that involves using numerical analysis to understand complex fluid behaviours. This normally involves building a three-dimensional model of a part or a component and analysing how a fluid or fluids interact. There are many models available in computational fluid dynamics, and this makes it very transferable between different industries such as aeronautical, heat transfer, power and multiphase flows. A common challenge that we see from our customers is that they are unable to represent their problem at full scale. This is generally because most test facilities are operated at lower temperatures and pressures due to safety and cost constraints. It's important for the customer to be able to understand from a technical and business decision-making perspective how their equipment performs. At TÜV National Engineering Laboratory, we solve this problem by helping our clients to understand the real-world conditions by building a 3D model and simulating as close to field conditions as possible.
My name is Sandy Black. I'm a CFD engineer at TÜV National Engineering Laboratory. I've been working for TÜV for around about 3 years and I have about 10 years experience in the field helping customers solve issues on fluid flow problems. One of my main areas of focus at the minute is the analysis of flare gas systems, both from a metering perspective and a combustion perspective. Flaring is the burning of waste gases through a flare stack or combustion device. It is primarily used for safety. It is used in the event of preventing any overpressurization of equipment in the facilities. Flare gas emissions are tightly controlled in the UK and other parts of the world due to their detrimental impact on the environment. Flare gas typically contains methane, which is a far more potent greenhouse gas than CO2. CO2, or carbon dioxide, is a product of the combustion of methane and is arguably an environmentally better option than releasing methane straight to the environment. In order to determine the quantity of gas being flared, it is important to have a metering system that can measure to an acceptable level of accuracy. Typically, these are ultrasonic meters. These ultrasonic meters require a set of ideal conditions in order to work properly. Most of the time there is limited space on site and these can be installed in a non-ideal location. What we typically find is that they are installed in a non-ideal location, and what we can do is we can construct a full 3D model of the system and model what the difference is between an ideal situation and an as-installed situation. This then gives the user an understanding of their metering error, and as such we can provide certain correction factors to help understand the difference between the two. When flare gas is released through a flare tip and ignited, it produces a nice stable flame under ideal conditions. However, there are other environmental factors such as wind or humidity or temperature that can actually impact the stability of this flame. For example, at high wind speeds, the flame might lean over and start attaching to the side of the flare tip. This can cause the flare to stretch and actually burn quite inefficiently. With that, we actually end up releasing more methane than we think we do. Now, this is quite difficult to measure because these flare tips are typically hundreds of meters in the air. So to get a drone or a probe up there is incredibly difficult. So at TÜV National Engineering Laboratory, what we can do is we can use CFD. We can couple that with detailed combustion chemistry and put it on our high-performance computing cluster and simulate different conditions and different scenarios as to what might happen. So we can give our operators an understanding of exactly how well that combustion is burning and how much emissions they are releasing to the environment. At TÜV National Engineering Laboratory, our CFD modelling approach provides an independent and impartial insight into problems involving fluid flow. which helps our customers develop solutions for their business needs.